Hello and welcome to Section 3 of Riverbed's RCSA exam preparation. I'm Bob Ashmore. I'm a Channel SE here at Riverbed. Let's get right to it. In-path configurations. In-path configurations refer to environments where we place the steelhead appliance between the switch and the router and physically cable the device with those two devices. When we do that cabling, we should be sure to use the correct type of cable. So when connecting to a switch, we use a straight-through cable, and when connecting to any other type of device, including another steelhead, we use a crossover cable. Please think of the steelhead as an endpoint device when cabling. When we do configurations of a steelhead appliance in a physical in-path environment, we usually are able to answer simply 20 questions. Those 20 questions are listed here. There are, however, environments where we need to do more than the simple 20 questions. Let's look at those type of situations. You can get away with doing just the 20 questions if you've got a single in-path interface being used. Also, if there is only a layer 2 network on the LAN side of the steelhead. Also, if we are not using any type of 802.1 trunk VLANs, and if what we're doing is all physical in-path, we're not trying to do any logical in-path configurations. So let's dive into the particulars of these types of configuration examples. The first is when we have multiple WAN links configured through a single steelhead appliance. In those situations, we need to make sure that we turn on the additional in-path interfaces. By default, those interfaces are not turned on, so they will not do any optimization. Traffic will be simply passed through. How do we turn on those devices? We go to the Configure Optimization General Service settings, and we enable the additional in-path interfaces that we wish to use. Also, we need to configure the IP address, the subnet mask, and the default gateway for those other in-path interfaces. We select the in-path interface that we want to configure, and then provide the required information in the field. Next, let's talk about the problem of packet ricochet. Packet ricochet occurs when you have a layer 3 network on the LAN side of the steelhead. Imagine packets are coming from the network, they're passing through the router, headed towards the steelhead. The steelhead grabs that packet and then needs to de-optimize it and send it to the destination device. Let's say, for example, the mail server. In order to get to the mail server, if there's a layer 3 network with a separate subnet from the in-path interface of the steelhead, then the traffic is going to go to the default gateway, which usually is the interface on the router. In that case, traffic's going to bounce off the router again and then go through the steelhead again, causing both of those devices to do extra work, which is suboptimal. To avoid this problem, we can do either of two things. We can configure static routes, or we can turn on a feature called simplified routing. Static routes are configured under Configure Networking and then the in-path interface. We list the different subnets and the physical gateway that we use to get there. Next, we can turn on simplified routing. We can do either of these or both. Simplified routing is by far the easiest way to go. We do that by going to Configure Networking Simplified Routing and select All from the pull-down menu. Next, let's talk about in-path deployments where we have multiple VLANs. When we're talking about multiple VLANs, we're talking about VLANs being trunked through the steel heads, and we will optimize all of those VLANs. However, it's important to understand that the in-path interface's IP address needs to reside on a VLAN that makes sense. So we go into the configuration of the networking and the in-path interface. We go down to the VLAN ID tag and we set the VLAN ID appropriately. Next, we need to talk about visibility modes. Visibility modes refer to what the traffic looks like on the inner channel between the two steelheads. Riverbed has the capability of making that traffic look however the customer would like it to look. So by default, and what 90-some% of our customers use, is a mode of operation called correct addressing. Correct addressing refers to using the source and destination IP address of the steelheads when we're talking about the traffic that travels between those two devices. So, traffic traveling from the client to the server has a source and destination IP addresses. The outer channel headers look exactly the same on both sides. However, on the inner channel, the traffic uses the source and destination IP address of the in-path interface, and everything runs over port 7800. The problem that you may run into with this type of configuration is if your customer wants to do analysis of the traffic between the steelheads. Maybe they want to charge back a division based on destination IP address. Maybe they want to keep track of how much traffic runs over a specific port because they want to know what application that is. And instead of doing the monitoring either at the client or the server side, they're doing it in the middle of the WAN. That is not typical, but sometimes it's being done. So in those environments, we need to provide some sort of spoofing. The first type of spoofing is called correct addressing with port transparency. What we do in a port transparency environment is we spoof the port number. So the traffic on the inner channel, in this case running over port 80, looks like it's going over port 80. Remember, the source and destination IP address is that of the steelhead on the inner channel. Only the destination port is spoofed in the inner channel. Next, if we want to provide full transparency, that's done by spoofing the entire header information with regard to source, destination IP address, and destination port. That's provided on the inner channel, matching what is available on the outer channel. Keep in mind that this can be problematic. Because the source and destination IP address are that of the actual client and the server instead of the steelheads, if there is an unknown routing configuration that allows traffic to go directly to the server and bypass the steelhead, you will have traffic showing up at the server optimized that the server won't be able to understand. For this reason, we strongly recommend you use correct addressing to avoid those types of problems. However, as we discussed, if your customer requires port transparency because he's looking at port information between the steelheads, then we recommend you use port transparency. However, if your customer needs source and destination IP address and port visibility over the wide area network, then we'll use full transparency. Just please be aware that we need to make sure we completely understand the routing environment and that the steelhead is able to intercept all traffic that it should. Configuring WAN visibility is done in in-path rules. Notice the pull-down menu near the bottom of the screen allows you to set the visibility mode. This means that I can configure a different visibility mode for my HTTP traffic from the traffic that's NFS, for example. Next, let's talk about logical in-path configurations. Previously, we talked about physical in-path configurations. Now we're talking about logical in-path configurations. Those are environments where we're using WCCP or policy-based routing or some type of layer 4 to redirection as we would experience with an interceptor. When we go through the 20 questions in the jumpstart configuration, we answer them all the same because it is a form of in-path configuration. So when you get to question number 12 or 13, which asks if you would like to enable the in-path interface, we say yes and proceed as we would in a standard physical in-path configuration. Next, we want to make sure that we enable L4, PBR, WCCP support in the optimization general service settings. When we talk about WCCP version 2, let's go through some of the basics. This is a proprietary protocol created by Cisco, which is used for redirection of traffic. It can be done by either rewriting the MAC address, this is known as layer 2 redirection, or by doing GRE tunneling when the redirecting device and the cache engine, as it's referred to, are separated by a layer 3 device, such as a router. We are able to redirect what's known as interesting traffic using an ACL on the redirecting device, such as the switch or the router. And we define service groups 61 and 62 to mimic what Cisco's QA department uses to test this protocol. Remember that we're going to physically cable to the WAN 0 port, and WCCP provides a form of high availability in that multiple steelheads can be connected to WCCP groups, and the router switch redirecting device will automatically load balance rudimentarily across those different devices. As you see here, the basic topology involves turning on IP WCCP on the router and creating groups 61 and 62 with redirect lists that are defined by ACLs. And then we go into the interface and specify that we want to do redirect in, meaning that traffic coming into the interface gets redirected. Some of the best practices include the following. Always check the iOS version. iOS version and WCCP are very sensitive. There are only specific versions of iOS that support WCCP correctly. Also, we strongly recommend that you check any design involving WCCP with a Riverbed engineer. You always want to try to be layer 2 adjacent. You'd rather not do GRE tunneling, which can slow down the redirection. Also, we want to use redirect in statements versus redirect out statements. Redirect out statements require the router to process the packet more than once. Also, try to connect the steelhead onto its own subnet on the router or switch. We don't want the steelhead to be sharing a subnet, for example, with a cluster of servers. Configuring WCCP is done in the networking section of the configure portion of the steelhead GUI, as shown here. Next, let's talk about policy-based routing, otherwise known as PBR. PBR is used when an in-path configuration is not an option and when a WCCP is not an option, maybe because of the iOS version on the routers. Policy-based routing allows you to create rules to redirect traffic from the router to the steelhead appliance. The router is able to make sure that the steelhead appliance is up and functioning by using the Cisco Discovery Protocol, CDP. Remember, as with WCCP, when configuring for policy-based routing, we connect a cable, and in this case it would be a crossover cable, to the WAN 00 port on the steelhead. Some things we should know, caveats with regard to with PBR in this case, refer to the fact that certain pieces of Cisco hardware do not support the verify availability. So in those environments, we need to turn on tracking or the IPSLA command. And the correct command to turn on CDP, which you may use even in environments where you are not using policy-based routing, is in-path CDP enable. So we've talked about in-path, physical in-path configurations. We've also talked about logical in-path configurations. Now we're going to talk about out-of-path, or what's commonly known as server-side out-of-path. We refer to it as server-side out-of-path because this only works on the server side. You cannot have an out-of-path configuration on the client side, because the client side is where the auto detection occurs of the steelheads using the three-way handshake. So once the naked SYN shows up on the client-side steelhead appliance, we use a fixed target rule to redirect the traffic to the IP address of the primary interface of the steelhead next to the server. This way, the traffic is destined for this mail server will be intercepted by the steelhead on the client side, which will then point the traffic at the primary interface on the steelhead. The steelhead on the server side will then create a NATed connection between that primary interface and the servers, and in this case, the mail server. That's server-side out-of-path. As if that weren't complicated enough, let's investigate how we would configure it. We configure server-side out-of-path by, instead of selecting the in-path configuration and saying yes, we're going to say no to the in-path configuration, and then we say yes to out-of-path configuration. Also, we make sure we enable out-of-path support in the GUI. However, if you do this in the wizard, that's not necessary. Notice that the in-path support is disabled in the GUI as well. Now, the next type of mode that we'll talk about is called hybrid mode. Hybrid mode involves doing physical in-path at the same time as we're doing server-side out-of-path. This combination of deployment methodologies is often used in steelhead mobile environments. And let's discuss. In an environment where you have branch offices that are connecting to servers, the standard in-path interface and physical in-path deployment would be used to optimize that traffic through auto discovery. Now, if I have traffic coming in through a VPN and I'm running Steelhead Mobile on laptops, we're going to use a fixed target rule on the Steelhead Mobile laptop, which is going to point to, again, the primary interface on the Steelhead appliance. Then traffic is NATed between the primary interface on the Steelhead appliance and the servers, which were the original target of the Steelhead Mobile client. So we have two separate types of deployments occurring simultaneously. Traffic is in no way interacting with each other. It's simply as if we use two different appliances to accomplish the same thing. Okay? We use the server-side out-of-path deployment for the mobile clients, and we use the physical in-path deployment for standard branch traffic. Hybrid mode is configured by enabling both the in-path settings and the out-of-path settings, but notice that we do not configure the logical in-path settings. If you turn on logical in-path, that will disable the LAN interface, which of course will not allow physical in-path configuration to work. So hybrid mode, again, is using physical in-path with server-side out-of-path. Okay, next let's talk about some high availability configurations. So these are situations where we want to make sure we maintain optimization, even in the unlikely event that power is lost to the steelhead appliance. The first one we'll look at is a serial in-path configuration. In this situation, we configure a master and a backup device. The master device handles the majority of the connections until it reaches its admission control level. Recall that admission control kicks in when you exceed the maximum number of licensed connections. So in a situation where a device is licensed for 1,000 connections, then the 1,001st connection goes in pass-through and will be accepted and optimized by the backup device. Also, in the unlikely event that the master device fails or has its power disconnected or something like that, then the in-path interface will switch to fail to wire. Fail to wire means that traffic will pass through automatically. Then the backup device will take over and optimize the traffic as it is destined for the wide area network. We configure failover in the GUI in the Configure Optimization General Service settings, and we define whether it's a master or a backup device, and then we specify the peer in-path interface of that other device, the IP address of the in-path interface of the other device. Next, let's talk about parallel configurations. Parallel configurations in an in-path environment allow us to support even the most catastrophic situation wherein we lose both a router and a steelhead or a switch on one line, one link, and the other devices are able to take over and support that conversation, and not only support the connection, but are able to optimize that connection. We do this by configuring something called connection forwarding. Connection forwarding allows traffic to be optimized even if it's asymmetric. This means that if the traffic is coming in on the left side here and hitting steelhead A, then goes up to the network and returns through steelhead B, connection forwarding will return that session back to steelhead A so that the conversation can continue to be optimized. Remember that we need one steelhead to optimize the connection. Each connection has a single steelhead that it is assigned to, and that conversation list is shared between these two steelheads in this type of failover configuration. Connection forwarding is configured here in the enable connection forwarding list, and then the neighbors are defined below. Additionally, we'll want to configure link state propagation. Link state propagation propagates the link state across from the LAN interface to the WAN interface and vice versa. This is beneficial on network equipment that uses loss of link to trigger convergence. So, for example, if the router connected to the WAN interface fails, then the steelhead recognizes this and brings down the interface on the LAN side so that the device connected there, maybe the switch, will show that the link is down so that convergence can begin. Great. So we've covered the different types of deployment. Now let's go through some sample questions. The first question: which of the following correctly describe the combination of cables used in a fail-to-wire scenario for the interconnected devices? Assume that auto MDIX is not enabled on any device. So basically we're asking what cable goes to a router and what cable goes to a switch. We can never rely on auto MDIX, and we will recall that a straight-through cable connects to a switch and a crossover cable connects to the router. So the correct answer is C. Next, which of these are valid addressing modes for the steelhead? Remember that the three correct addressing modes include correct addressing, port transparency, and full transparency. Next question: a customer is enforcing QoS between the steelheads based on the destination port. So we need the destination port to show up on the packets between these two devices. Which mode will provide that visibility? Port transparency, of course. Next, assuming that the steelheads have port transparency configured for this connection, what would be the destination port between the two steelheads? So remember, with port transparency, the port is preserved or spoofed. So since the outer channel is running traffic over port 80, the inner channel will as well. The answer is port 80. Next, which version of WCCP supports redirection of all types of traffic? WCCP version 1 supports redirection of port 80 traffic. WCCP version 2 supports redirection of all types of traffic. So your correct answer there is version 2. Next, what port needs to be connected in a server-side out-of-path configuration? Remember, when we're doing server-side out-of-path, we use the primary port. That's D. Next, assuming that the steelheads have correct addressing configured for this session, what would the destination port be between the two steelheads? Correct addressing. Remember that correct addressing uses the source and destination IP addresses of the steelheads, and then uses port 7800 on the inner channel. So with correct addressing, your correct answer here is A.